Hi guys, so this is the part 2 of the single degree of freedom or vibration system derivation. So last time when we left it off, we left it as zeta is equal to 2m omega n, as in omega n is equal to natural frequency, m is the mass of the system, and c is the Coulomb friction. So I'm just gonna rewrite the first equation again. So I said m double dot x plus cx dot x plus kx is equal to 0. That's our equation of motion. Equation of motion, and we divided the entire equation into x is equal to, not divided, like we express it as minus c over 2m plus or minus c squared minus 4mk divided by 2m. So this is the equation we have right now. Now what I'm going to do right now is replace the c with the term of c is equal to 2 zeta m omega n. So I'm going to write it on the next page. So x is equal to c over 2m plus or minus c squared minus 4mk divided by 2m. Hold on a second. Let me check if I can spot properly. It's okay. Yeah, I was just checking if it's on the right page size. No, the zoom is on the right location. So, and c is equal to, just now we said c is equal to 2 z m omega n. So x is equal to 2 minus 2 zeta m omega n divided by 2m plus or minus, so that's I have a c squared in it, so this entire term is going to be squared. So for now I'm going to put 2 z omega n m squared minus 4mk divided by 2m, just for now. So I can simplify this term as in, so this 2 and 2 cancels out, this m and m cancels out, so it's going to be minus zeta omega n plus, so in the denominator I have 2m. If I want to take this denominator inside of the root, so it will become as, so let's write at the top because it's not going to change. So 2 zeta omega n m squared minus 4mk. So if I take this inside of the square, it will become 4m squared. So it's like saying, like, so root of 4m squared is equal to 2m. So that's exactly what's happening in here. And also I'm going to expand this one, so it's going to be very simple. So x is equal to minus omega n plus or minus 4m squared at the bottom, so it's going to be 4mk, so it's going to be 2 squared zeta squared omega n squared m squared, everything inside the bracket. Perfect. Now 4 is a common term in here, so we can cancel out 4. I can take out the m as well, but in here I have an m squared, in here I have only 1m. So we're going to do a little bit tossing around with variables. So I said previously that omega n is equal to, so omega n squared is equal to k divided by m. This is the natural frequency, and this is the spring constant, and from the Hooke's law, and this is the mass of the system. So k is equal to m omega n squared. Just simple, changing variables. So let's rewrite this equation again. So this equation, so x is equal to minus zeta omega n plus or minus inside the root. So in the denominator I have 4m squared. So first term is omega n squared m squared minus 4m. I'm going to replace the k with m omega n squared. So let's rewrite it one more time. Take out the bracket, minus zeta omega n plus or minus. Inside the bracket I have 4m. So in the denominator I have 4m squared. So on the denominator 4 zeta omega n squared m squared minus 4m squared omega n squared. So you can see like there's a lot of like terms in there we can cancel out. So let's do it. So minus zeta omega n plus or minus inside the root, the denominator 4m squared. So I can take a common term as 4m squared in the both denominator. So 4m squared. So in here it is just going to be zeta squared omega n squared minus omega n squared. So this 4m and this 4m will cancel out. Also, as you can see, I can take omega n squared outside of the entire equation. So I'm going to rewrite everything again in the next page. So x is equal to minus zeta omega n plus or minus. I'm going to be rewriting everything, m squared zeta squared omega n squared minus omega n squared divided by 4m squared. So I just said in the previous page, this and this will cancel out. Minus zeta omega n plus or minus. Again, I'm going to take a omega n squared. If I take a common factor, so it's going to be zeta squared minus 1. This, so it's like, think about like a 4. So if I have a 4 in here, no, think about x squared. So if I take the root of x squared, so it's going to be x. So it's going to be minus zeta omega n plus or minus omega n 1 zeta squared minus 1. Now this is where everything gets complicated. So this term, this is the most important term. So I'm not going to go into detail about how, for now, why is that happening, but in later tutorials I'll be doing control systems, or even in here there are 3 systems called damp, underdamped, and overdamped. So this result, damped, underdamped, and overdamped, is totally based on what's the outcome of this value. So it can be 0, it can be positive value, or it can be a negative value. If it's a negative value, then it's going to be results are going to be in the imaginary roots. So that's when we use it in the PID controllers. So let's skip that topic, and so we have, so our result is x is equal to minus zeta omega n plus or minus omega n. So for now we like to keep it as, let's pretend this is like, so we're gonna keep it as positive for now. And also I said zeta is a ratio, defines c over t omega n m. So also as a c divided by c critical. So it's theoretically it should be, this should be the higher value, is this should be high and this should be low ratio. So it's a negative value, so it's going to produce as a negative value in here. So why do I, sorry, in here it's going to produce a negative value. What do I mean a negative value? Let's say if I have a, let's say the ratio is equal to 0.9, and inside of the root I have 0.9 square minus 1, which is less than, this is less than 1, however it's going to be less than 0, so the results will be minus, so the 0.9 squared is 0.81 minus 1 is going to be 0.19, so minus 0.19. So we can't, usually in the math we can have a negative answer root, so it's going to be root of 0.19i. So let's just leave it this part for a moment, because that's how we define a vibration, and this is something I just went in deeper. So right now our results have excess two results, so either it's positive or either it's a negative value. In differential calculus, when we have second order differential calculus, when we have results like this, we use, I believe, complex conjugate. So what complex conjugate is, let me go to the next page. So there are three types of results in the differential equation, and I'm only going to focus on complex conjugate right now. Maybe later on I will focus on the rest of the results, but they're pretty easy. So let's just, okay, they're really easy. So let's just say I have like a 1x squared plus 3x plus 2 is equal to 0. So I'm just saying that for one of my mass, or one of the system, I have mass is equal to 1 kilogram, c is equal to 2 Newton meter. Is it Newton meter? Newton. I think so. Okay, I'll check it out in about that. So k is equal to 2 Newton meter. Yeah. Oh, this is something wrong in here. So let's just say Coulomb friction is 2. So what I was saying is, this is 3. So if I have, so the system is going to look like x double dot 1 plus 3x dot plus 2x is equal to 0. So when I solve for the system, so x is equal to minus b plus or minus b squared minus 4ac divided by 2a. So a is equal to 1, b is equal to 3, c is equal to 2. So x is equal to minus 3 plus or minus 3 squared minus 4 times 2 times 1 divided by 2 times 1. So minus 3 plus or minus 9 minus 8 divided by 2. So which is equal to minus 3 plus or minus, so 9 minus 8 is 1, so 1 divided by this, so again it's 1 divided by 2, so x is equal to minus 3 plus 1 divided by 2, or x is equal to minus 3 minus 1 divided by 2. So either x is equal to, so in here is going to give me minus 1, or x is equal to minus 2. So I have two results, but even though they are negative results, but they are not complex results, they're real results. So these are real values. So if we have real values, going back to this form for the results of the x, so how we do in the differential calculus is we say x is equal to c1 e to the power of minus 1, let's say t, plus c2 e to the power of minus 2t. So the reason I put t is because x is represented in terms of t, because how far the distance he went according to the time, or for the given amount of time. So that's what I say x. So c1 and c2 are two constants. We don't know yet because we don't know the initial conditions of the system. But this thing, so -1, -2. So what do you do is, like, whatever value you get, you just put it in there. That's it. Let's say, for instance, when you do it, you get a result like x is equal to -1, and also x. Let's say this is x1 and x2, and x2 is also equal to -1. So probably everyone knows this case. So if that's the case, so xt will become c1 e to the power of -1t plus c2x e to the power of -1t. So only thing, if these two results are the same, only thing you do is, like, put an x in there. So this is case 1, this is case 2, and this third thing that we're going to focus on is the case 3. Case number 3. So right now, let's just say, for instance, you do the previous node way, like calculating x minus b plus or minus blah 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 root divided by 2a, and what you get the results is, let's just say, for instance, x1 is equal to, I'm going to use the term m and n just for example. So let's say m plus ib, and also x2 is equal to m minus ib, or should be n, let's say. So why do I have an I in here? Because I have a negative value inside of the root, so that's why I have to put an I in there. So this is where it gets tricky. It's not exactly tricky, it's just like they have one equation that you follow all the way around. So what they say is x is equal to, these m are the same in all the results. Only thing is changing is I. That's the one is changing. Oh, I could write it as like these two. I can just write as like x is equal to m plus or minus in. So what will become is like e to the power of minus mt, or mt. So e to the power of mt cos whatever n that you have, that you just put it in here. So nt plus sine nt. Also, there's two constants, so c1 and c2. Let me write this again. So x is equal to e to the power of mt c1 times cos nt plus c2 times sine nt. So that's all you do. That's how if we get a complex number in the results, that's how we solve the differential equation. Now, let's go back to our original equation, which we solved for the vibration. So we solve x equal to minus zeta omega n plus or minus omega n 1 minus, that's what we wrote, zeta square. So in our case, m is equal to minus zeta omega n, then n is equal to omega n root of 1 minus zeta square. Or when we were deriving it, it came out to be omega n zeta square minus 1. That's how when we deriving it. We just gonna assume this for now. This is the only term that we're gonna use. So as I mentioned before, remember we got a negative value in here. So when I use a zeta is equal to 0.9, we got a negative I. So we're gonna use that term. So this is how you write equation, but sometimes when you solve it with the differential equation, this is how you use it. But there's another way called Euler's method. We will do it another way. So the actual results are going to be like, let's say, m plus or minus in, because we assume it's giving an imaginary value. x is equal to e to the power of m is equal to this minus zeta omega n t, big bracket, c1 cos, this whole term will be represented in here. So omega n 1 minus e squared times t plus c2 sine omega n 1 minus e squared times t. And this is the basic equation of the motion of a free vibrating system. So in MATLAB, what we do is we know the initial conditions. We know the mass of the system, we know the K of the system, we know the C of the system, and we also know the how long we're gonna run this system, or the time range. So let's say t is equal to 30 minutes, or let's say 20 seconds, or something like that. So time, total time, we're gonna test it. So what we do is simple. So we know the mass and a K, so we can find out the omega. So omega is equal to, omega n is equal to root of K over m. Define that value. Second thing we do, we find the zeta is equal to c divided by 2 omega n m. So we find the zeta. Now these two become a little bit tricky, and then in the next video I'm going to take up an example and I'm going to show you guys how to calculate the C1 and C2. Just for now, I'm saying that I also know the initial condition. So let's say time when t is equal to 0, it might have the speed of, let's say, v0 is equal to, let's say, 2 meters per second, and also initial displacement of this body, let's say x is equal to 1 meter or something like that. So initially it was not at the center, it was like a little bit moved. So we have the initial condition, which will help us to find out constant C1 and C2. So you have all this information. All you do in a MATLAB, you create one array matrices with t is equal from let's say t is equal to from 1 to 20 seconds, and let's say with the increment of 0.5 seconds, sorry, 0 to 20 increment 0.5 second, you have create a matrices and you allocate it, and you start plugging in, like do like a do loop of like putting in each and every value, t is equal to 0 or something like that, putting values in here, and over the time you will see like, and also you create the x's as in the same array as the t. So you will have a value and you plot those values, and that's how we get the motion of the free vibrating system. So this is the basic rundown of how you derive that equation. In the upcoming videos I will also show you guys why that x dot came up to be, and also the damp, underdamp, overdamp system, plus how you calculate C1 and C2. Thank you for watching my video, and I'll see you guys in the next video. Have a good day.